Hey, Davion. So these are the questions that you were stuck with. Very quickly, though, these questions are actually answered on some of the videos that we have posted. So let me just show you those really quickly. If I go to modules on our course site, and then here we are in weeks 1 and 2. If I click on lectures, then this is the PowerPoint lecture notes, and you've seen those already. But if you click on video lectures, here are some videos that actually go through some of this content. So the lecture that you're actually looking for in terms of latitude and longitude is going to be this one, this second one, Earth Representation Full Lecture. And I go through latitude and longitude and time zones and things of that nature. But if you want to skip that and go into very more specific stuff, this video right here, latitude and longitude, covers all this. It talks about how you find your latitude, how you find your longitude, how you determine time zones, things of that nature. That's all here on video number 3, and it continues on with video number 4 as well. And these are relatively short, so definitely go back and take a look at these videos. But in the interim, I'll directly address these particular questions, number 8 through 15. So let's start with question number 8. And it says if your time is 5 p.m., what time will be at a location 45 degrees west of your position? So I've got my sketch pad up here, and let me just sketch it out for you if I can find it. Here we go. So the question is, it's 5 p.m. and we want to know what time it is at a position of 45 degrees west of your location. Okay, so we're just going to draw this out. I always draw this out when I'm doing time zone questions. And this is 0 degrees. So this is the prime meridian. And remember, this direction is west, so that's the western hemisphere. This direction is east, so this will be the eastern hemisphere. If we go all the way to 180 degrees, whether it's west or east, it doesn't matter, then you find yourself on the international date line. And so this is sort of a picture. Well, keep in mind that the Earth is a sphere. So if I draw it this way, and if this is 0 degrees, then 180 is over here on the other side of the planet, and this would be the western hemisphere, and this would be the eastern hemisphere. So all I've done is I've sort of pulled the Earth apart. So this 180 is this and this by just pulling the Earth apart. Okay, so it says it is 5 p.m. At your time. It doesn't really matter where you're at. The question is, what time is it 45 degrees west of your position? So let's just presume that it's 5 p.m. over here somewhere. Okay, so it's 5 p.m. and we want to go west. So this direction is west, and again, this direction is east. And we're looking to go 45 degrees west. Well, every 15 degrees of longitude equates to 1 hour of time. So 15 degrees into 45 degrees equals 3. That means that 45 degrees west is 3 hours different than 5 p.m. The question is it 3 hours behind or is it 3 hours ahead? Well, anytime you're going west, it's behind. And anytime you're going east, it's ahead. So, for example, we live in the United States of America. This is it right here. This is the West Coast. This is the East Coast. And the difference is actually 3 hours. So, Western here is Pacific time, and Eastern here is Eastern time. So, if it's actually 3 p.m. Western or on the Pacific, then it's going to be 3 hours ahead on the East Coast, which would make it 6 p.m. And again, we know this because East is ahead. If we were here on the west side, or excuse me, if we were here on the east side and we went toward the west, it's 3 hours behind. We are 3 hours behind of our East Coast counterparts. So anyway, with this particular question, if it's 5 p.m. somewhere on the planet, we're just presuming here, doesn't really matter. If we want to know what time it is 45 degrees west, We know that that time is behind, and we know it's behind by 3 hours because, again, every 15 degrees of longitude equals 1 hour. So 15 into 45 is 3 hours of time difference, which means if it's 5 p.m. here, 45 degrees west would make it 2 p.m. Okay? So that's the answer to question number 8. Question number 9 is a little bit more specific and almost complicated, but not really. It says if it's 11 a.m. Saturday at a location 135 degrees east longitude, what time and day is it at 165 west? So let's take a look at that question. We'll clear the board. I'm going to draw this again, just like I did before. So here's the world. Here is 0 degrees, or the prime meridian. And we know, let me go back to the question, I've forgotten it. We know it's 11 a.m. Saturday at 135 east. So 135 east is going to be over here because this is the east side, this is the west side. So 135 degrees east, right here. And the time is, let's go back, sorry. The time is Saturday, 11 a.m. And so let's put that in here. So this is Saturday at 11 a.m. And we want to know what time and day it is way over here at 165 degrees west longitude. There's 2 ways to answer this question. We'll do the long way and then we'll do the short way. So if we count backwards in time, we know that if we go toward the west, we're going behind. We also need to know how many degrees of separation there are because remember, every 15 degrees of separation equates to 1 hour. So 135 to 0 is 135 degrees. Then 0 to 165 is 165 degrees, which means our total degrees of separation is 165 plus 135 or 300 degrees. So there are 300 degrees of separation between 135 east and 165 west. So this is 300 total degrees. Remember, 15 degrees per hour, so 15 into 300 equals 20, which means that 165 is 20 hours behind 135 east. So we can start counting backwards and go, okay, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3 a.m. And we went backwards from Saturday to Friday. So we know that the time is 3 a.m. and the day is Friday. It's 20 hours though. It's just a lot of finger counting. The simpler way to do it is to actually count ahead and not behind. Remember, we live on a sphere, so it doesn't matter if we go backwards or forwards, we're eventually going to reach the same place because we're on a sphere. So if I want to count ahead, I know that the time difference is not going to be 20 hours, but rather it's going to be 4 hours. And you might say, well, how do you know that it's 4 hours ahead? Well, if it's 20 hours behind, you have to be 4 hours ahead because there's only 24 hours in a day. So 20 hours behind, 4 hours ahead is 24 total hours. There are no more time zones on the planet. So I can count backwards if I want, or I can count ahead by 4 hours. So if it's 11 a.m. and I count ahead by 4 hours, it's 11, 12, 1, 2, 3. And I'm glad I did it this way because now I know it's actually not 3 a.m., it's 3 p.m. So 11 a.m. plus 4 hours gets you to 3 p.m. We cross the international date line. We go from Saturday to Friday. Now you may say, how do you know you're Friday? Well, that's because here's the international date line at 180. If you cross the international date line and go from the Eastern Hemisphere into the Western Hemisphere, then you actually gain a day. And you've got to set the calendar back. If you go from the Western Hemisphere across the international date line to the Eastern Hemisphere, then you lose a day and you got to set the calendar ahead. So because we're crossing the international date line from the Eastern Hemisphere into the Western Hemisphere, we know that we're setting the calendar behind a day. We're getting it back. So we're going from Saturday to Friday. We know that we're 4 hours ahead. So 11 a.m. plus 4 hours gets us to 3 p.m. So the answer is going to be 3 p.m. Friday. Okay, so that's the answer to question number 2, or in this case, number 9. All right, let's clear the board. Let's take a look at the next one. This says if it's solar noon at your unknown location, your chronometer or clock reads 8 a.m. and your clock is set to Pacific Standard Time at 1:20 West, what's your longitude? This is a little bit, I don't want to call it complicated, but it's certainly a little bit trickier. This goes back to the longitude problem and trying to figure out your longitude at sea, for example. The only way to really determine your location longitude is by using a good clock. And we know that because we just explored time zones. If, for example, we know it's 3 p.m. at 120 degrees west longitude, which is sort of where we're at on the West Coast, and if we went to 45 degrees east of us, which is 3 hours ahead, so 120, let's do this out. So let's say we draw a picture of the United States and it's 120 degrees west here. And over here is 120 minus 45, which is what, like 75 degrees west. Excuse me. Yeah, still 75 degrees west. So if we did this 120 west and over here is 75 west, and I tell you that it's 3 p.m. here and it's 6 p.m. here, you can clearly see that there's a relationship between time and your location. And that's, of course, because the Earth is rotating on its axis and we have different time zones. Because here's the Earth and then the sun is here. If you're here on the planet, then it's essentially solar noon because you're beneath the sun. But as the Earth rotates, these people over here, they might be at like 10 a.m. They haven't rotated into noon yet. So again, your location and your time go hand in hand. And that's ultimately what this question is about. So it's saying that it's solar noon at your unknown location. So it's solar noon at your unknown location. That's what the question mark is for. But if you have a clock and your clock is set to Pacific Standard Time, which is at about 1:20, and if it reads 8 a.m., we can actually figure out what time it is we can figure out what this longitude is. So again, at 1:20 west, we know that it's 8 a.m. We also know that it's noon at some unknown location. So let's draw this picture again. So here's the picture. Here's 0, which is the prime meridian. Here's 120 degrees west longitude. We just said that it's 8 a.m. And we know that noon is somewhere on this planet, and we want to know where on the planet noon is. So the first question you ask yourself is noon ahead, which is this way, or behind, which is this way, 8 a.m.? Well, we know that noon is ahead of 8 a.m., right? And so the question now becomes, how many hours is noon ahead of 8 a.m.? Well, if it's 8 a.m. here at 1:20, and if it's noon right here, that's 4 hours of difference. So our unknown location is 4 hours ahead of 1:20 west. Okay? So remember, every 15 degrees is 1 hour. So 15 times 4 is 60 degrees. That means our unknown location is 60 degrees east of 1:20 west. All right, we can put this now on our map. This is 0. This is 1:20. If we got to go back 60 degrees this way, 1:20 minus 60 is putting us at 60 degrees west. So the answer to this question is the unknown location is at 60 degrees west longitude. Okay, so you got the answer. Definitely go back, replay this video, and make sure that you're comfortable with it. But again, if you take a look at those other videos, I go over very similar problems. And so you're going to have more than one problem to take a look at. Okay, question number 11. I'm not going to give you the answer to this one. I want you to think about it. Okay, so I'm leaving that one off the table. Let's go to question number 12. It says you go outside and determine that the North Celestial Pole Star Polaris is 30 degrees above your northern horizon. So what is your latitude? Let's draw that picture. Here is the Earth. Here is the North Pole. Here's the South Pole. So SP, NP. North Geographic Star, or the North Celestial Pole Star, is above North Geographic Pole. And that star is Polaris. So Polaris is the North Star. Now, if you were standing at the North Pole, and if you looked straight up, then Polaris would be at your zenith point, meaning that the angle that the star makes with your northern horizon is going to be 90 degrees. Okay, let's say that you are standing right here, not at the North Pole, but let's say that you are standing at around 80 degrees of north latitude. Well, now if we draw this line, the north horizon line, and we took basically a protractor, and we were measuring the angle from the northern horizon to the North Celestial Pole Star, you can see that it's not 90 degrees. It's not a right angle. It's less than 90. And as a matter of fact, it's actually going to be 80 degrees. If you were standing here at, let's say, 60 degrees of north latitude, and if you were to draw a picture again from your north horizon to the North Celestial Pole Star, it's actually going to be 60 degrees. As it turns out, your latitude is equal to whatever angle your northern horizon makes with the North Celestial Pole Star or Polaris. So, if you go outside and you're at 30 degrees of north latitude, that means if you were to draw this north horizon line, the angle, let's draw it again over here so you can see it a little bit better. Here's the North Celestial, well, here is the north horizon. Here's the North Celestial Pole Star. That angle would be 30 degrees. Again, the angle that the North Celestial Pole Star makes with your northern horizon is your latitude. So if you go outside and the North Celestial Pole Star is 30 degrees above your northern horizon, your latitude is 30 degrees. Simple as that. Okay? All right, next question. What city does the prime meridian run through? What longitude is the international dateline? Again, here we draw a picture of the world, the globe. We'll give it some three-dimensional texture. Here's the prime meridian. It's at 0 degrees of longitude. It runs from the North Pole to the South Pole. Although it goes through a number of various cities, the most famous one, of course, is Greenwich, London, England. So Greenwich, London, England, and that's where the prime meridian runs through. That is 0 degrees of longitude. If we, again, want to know what the international dateline is, I mentioned it earlier, but let's draw this picture again. But now we're looking straight down from the North Pole. So here's 0 degrees, the prime meridian. If we go 180 degrees from the prime meridian, either from the west side or the east side, it doesn't matter. You're going to land over here at 180 degrees. 180 degrees is the location of the international dateline. And again, if you cross over from the Western Hemisphere into the Eastern Hemisphere, across the international dateline, you're losing a day. You got to set the calendar ahead. If you're going from the Eastern Hemisphere into the Western Hemisphere, you get to set the calendar back so you gain a day. And that's if you cross the international dateline. All right, a couple more questions. Number 14, on a topographic map, what do closely spaced contour lines indicate? So let's say that we've got a map, and again, we'll take a look at the United States, and let's say that we've got this contour line here, and we have another contour line here, and here's another one, and here's another one. And let's say that these contours are 4 feet apart. So this would be 4 feet of elevation. Here's another 4 feet, so this would be 8 feet of elevation. This is 12 feet of elevation, and this is 16 feet of elevation. So each contour line represents elevation on a map. If I want to know what closely spaced contour lines mean on this topographic map, it has everything to do with the steepness of a slope. So the distance from here to here is 4 feet of elevation change. The distance from here to here is 4 feet of elevation change. The distance from here to here is also 4 feet of elevation change. And the distance from here to here is also 4 feet of elevation change. So you can see that right here, changing 4 feet takes a longer distance than here. So let's take a look at the side view. Let's say that this is point A and this is point B. This is what it would look like. Point A, point B. We go 4 feet of elevation, but it's not a particularly steep slope. Let's take a look at this though over here. This is point C and this is point D. So here's point C and here's point D. We're going 4 feet again, but notice now that the slope is much steeper because we're doing the 4 feet over a shorter distance. So on a topographic map, closely spaced contour lines indicates greater change over a shorter distance. So in this case, in terms of a topographic map, this would mean that we've got a steeper slope. Okay, finally, question 15, in degrees of longitude, how wide is each time zone? And again, I mentioned this already. This is the Earth. Here's prime meridian. We're going to 180, which is international dateline. Here's 180, international dateline. There are 12 time zones this way, 12 time zones this way. There are 24 time zones on the planet. Each time zone is 1 hour, therefore there are 24 hours in a day. We live on a sphere. A sphere is 360 degrees. 180 plus 180 is 360. So this whole thing is 360 degrees. There's 24 hours in a day. So 24 into 360 equals 15, which is why 15 degrees of longitude equals 1 hour of time. So again, 24 time zones, each one is 1 hour, each one is 15 degrees longitude wide. That's it. Okay, so those are questions 8 through 15. Again, if you have any questions further, please let me know. Also, once again, refer to these other videos that are here. I go through this as well. I take a little bit more time to do it, but I definitely specifically talk about latitude and longitude, and I go into detail. So these videos are extremely helpful. These, again, are the small bite videos. This one is the longer presentation, but these ones are short and sweet, and they get right to the point. All right, man. Again, if you have any other questions, please let me know. Take care, and I will talk to you later. Bye-bye.